In this example, what we're going to be looking at is we're going to be looking at a single slit. Now, we've looked at Young's double slit experiment. And in this case, what we're going to be looking at is a single slit experiment, which is what I have drawn here. And how this works, and I didn't draw it out, but how this works is you have a wave front that's going to be incident upon this single slit. And at this point, what happens is only a certain amount of light is going to be allowed through. So this would be the width of that slit. Now, it's difficult to envision, but what happens is that light at the top of the slit will travel at a different distance than light at the middle of the slit, so long as it hits the exact same point on the screen. And what happens is as that wave front hits, and some part of that light is going to travel a little bit different distance than another part of that slit, what happens is you get constructive and destructive interference. And so what I've marked here is I've actually marked two destructive interference fringes or dark fringes that are going to occur. Now, W happens to be the width of that slit. The angle is going to be the angle to the first dark fringes. They're first order fringes, so I've labeled them M1, M1. And they're going to be a particular distance from the center of that slit. So the yellow line represents the center of the slit. Now, there's a screen here, and the distance of that screen is going to be 40 centimeters or 0.4 meters. And the question reads as such: light of a wavelength, so lambda, is equal to 675 nanometers, illuminates a single slit of width, so the width of the slit is equal to 180 microns. What is the angle of the first diffraction minimum? So when we talk about the first diffraction minimum, we're talking about the destructive interference. And the equation we're going to use is m lambda is equal to W sine theta, where m is going to be the order, right? So m is equal to the order. Lambda is once again going to be our wavelength. W is the width of the slit. And then theta is going to be our angle. And so for this first one, it asks us, we need to find the angle of this diffraction. So the angle of this diffraction. So our sine of theta is going to be equal to m lambda all upon W, which is equal to, we're looking for the first order. And our lambda is 675 nanometers divided by, now the width. The width in this case is 180 microns, or that's going to be equal to 100 times 10 to the third nanometers. You want to make sure you get this in the exact same units. So the nanometers cancel, we have a unitless number, and therefore the sine of theta is equal to 3.75 times 10 to the negative 3. Therefore, our theta, take the inverse sine of that, is going to be equal to 0.21 degrees. It's going to be equal to 0.21 degrees. Now, the second portion of this problem says, if a screen is placed 40 centimeters or 0.4 meters away, how far is the dark fringe from the center of the diffraction gradient? So we want to find y. So we're going to find y. Not findy. It's kind of goofy. We're going to find that height or the distance y. Well, we're going to use a trig function for that. And so if we're using a trig function, we can use, for instance, tangent. So the tangent of theta, right, is going to be opposite over adjacent, which will be y divided by L, all right? Or we can say that L, tangent of theta, is equal to y. our y is 0, or I'm sorry, our L is 0.40 meters, and then this would be the tangent of the theta we just found of 0.21 is equal to y, and that is equal to 1.5 times 10 to the negative third meter. Or we can multiply this by 1,000 and realize it's 1.5 millimeters. So this height here, or the distance here, the height is going to be 1.5 millimeters. If you have any questions on the single slit experiment or anything else in this chapter, please let me know.